have 2 more minutes. In the meantime, I think we'll introduce Matjaž, and then he can get straight into his talk. So Matjaž has been working with David Deutsch on a paper about the so-called Popper-Miller theorem, which kind of recasts Bayesian updating in a new light. So many people are very keen to see Bayesian updating as a way to attribute probabilities to scientific theories. And Matjaž and David are actually very critical of this view. And using the Popper-Miller theorem, they're able to show that it is the usual interpretation, as Matjaž puts it, is not quite correct. That you cannot actually use these Bayesian probabilities to say whether or not a scientific theory is correct or is likely. So as we said, you're going to present, and then afterwards there'll be a Q&A.
So thank you. So it's a pleasure to be speaking to the Oxford Karl Popper Society. I suppose that there is no better venue to talk about a theorem that was proved by Popper than a group of people especially interested in his work. This talk, however, does not sort of presuppose any sort of familiarity with his work, while at the same time sort of tries to relate this theorem, I suppose, in kind of the broader context, like tries to relate it more with sort of the rest of his writing that I'm sure you're sort of familiar with. Now, this theorem that I'm going to talk about is fundamentally a probability paradox. And as I think Scott Aronson at some point pointed out, probability paradoxes never take more than 2 lines to prove. Sort of all of the effort with probability paradoxes is in kind of getting yourself to a certain perspective where basically the probability fact in question sort of shows something counterintuitive. And this is very much also the case with this theorem. When they originally published this theorem, it was in this sort of short article in Nature in 1983. There was a huge amount of responses to this, and there was sort of a lot of confusion. I think that the way we sort of got interested in it was that, well, we couldn't understand it. And eventually we did, and thought that this might be sort of a thing that you know, should be better explained, especially sort of in light of responses that were both sort of critical and supportive of it. But perhaps just sort of as a preamble, so one of the things that is, I think, usually sort of kind of brought up as a question about Popper and his views on things is simply like in what way do they so he was quite critical of all of these sort of probabilistic approaches to knowledge. But it's not really obvious sort of from the outside why that would be, because like isn't something like, say, you know, this sort of Bayesian way of thinking, isn't it basically just a kind of a natural extension of his view? Because, you know, if say an observation contradicts the theory, you know, Bayes' theorem tells you that the probability of that theory should now be 0, or, you know, at least in kind of the non-problematic cases. But then on the other hand, Bayesianism seems to give you something more, which is that you basically, you know, also can seemingly use this evidence to kind of change the status of theories that you sort of haven't quite made up your mind about yet. And so, what therefore is the problem? And next slide. Hello. Okay, so yeah, so and so the chief reason for why he was so sort of skeptical of these sort of probabilistic approaches is this idea of content. So the idea is that just like, you know, one might regard some theories as more likely than others, there is also a sense that perhaps some theories say more than others. So, you know, a theory A might say less than, you know, the theory that says A and B. He was interested in this for various reasons. One of them was to try to make sense of this idea of the progress of science. The other reason was that there was this whole idea of kind of degrees of falsifiability that played a role in sort of all of this. he was therefore kind of interested in this concept. And there was also this idea that one could sort of try to construct a measure of content, a measure, just like, you would kind of have a probabilistic measure of theories, you would have sort of a measure of content of a theory. And one of the sort of the main realizations that kind of emerged out of that thinking was that the constraints that this content measure would have to obey are in some sense the same as that probability would have to obey. As he put it in some of his writing, a high degree of probability is really just a high degree of sort of logical weakness. So the idea is that the less a theory says, the closer it is to just being like a tautology, and the more a theory says, the closer it is in some sense to just being a contradiction, which kind of says everything. So one of the kind of consequences of this is that if you sort of imagine a Bayesian agent that has some theories and thinks some of them are more likely than others, and thinks that these sort of different theories obey the probability calculus, you could kind of reinterpret the state of that agent as basically saying, well, this agent kind of has these theories, he thinks some of them say more than the others, and he kind of prefers to think about or is willing to bet more on those that in some sense say least, according to that measure. Now, why is that a problem? Well, it sort of goes against some of the other ideas that Popper had about sort of the nature of scientific progress. The idea there was that sort of scientific progress, sort of proceeds from kind of theories with less content to theories with more content. Like, so I mean, kind of one analogy to draw here would be that if in a world kind of entropy is thought to be constantly increasing, but kind of the entropy of scientific theories is supposed to be decreasing. So the idea is that one kind of proceeds to theories that are true in ever fewer possible worlds, rather than it's kind of as science develops, rather than sort of on theories that are sort of ever vaguer, ever kind of more tautology-like in light of experience. Now, this is not exactly strictly speaking true. So for example, if you think about something like Newton's theory, if you start out with that and you then discover the conservation of energy, a conservation of energy is in some sense a more kind of a high entropy statement than Newton's theory, right? It is true in more possible worlds than Newton's theory is, and nonetheless discovering it could be this sort of could constitute sort of major progress. But kind of in broad strokes, it does feel like sort of the story of science is very much that of kind of progressing from sort of low content theories to sort of high content theories. And indeed, that also seems to be the case with just sort of how psychology and persuasion work. So, if somebody appears in court and wants to make the case that somebody committed a crime, what you present normally is a very, very specific story about how this happened that explains all sorts of other things. And you do that despite the fact that it is much more likely that the person did it as opposed to just doing it in any particular way. And there is also, I think that this phenomenon is also to some extent realized in various parts of the psychology literature, except in some of them it is deemed to be a cognitive bias. So I'm sure many people are familiar with this sort of famous example of a cognitive bias called the conjunction fallacy. And the way the conjunction fallacy works is basically just like that. So people are given a set of facts, and then they are given sort of a theory A, and then they're given a theory A and B, where A and B explains the facts, but A by themselves does not. And people reliably declare this A and B to be more likely than A, in contradiction with sort of the probability calculus. Now sort of they think of this as a cognitive bias. Sort of these sort of Popper-inspired thinkers think of it as sort of fundamental to science. One could sort of think of it, one way or the other, but that is kind of this is kind of the context from which I think this whole sort of skepticism of probability as it relates to knowledge kind of emerged. And there are, of course, many arguments and counter arguments that could be made to the story that I just told, but that is kind of the idea. And now we go to sort of closer to kind of the theorem we were supposed to talk about. So next slide. Okay, So now this theorem we've been sort of thinking about, and that this talk is sort of about, really sort of revolves around this sort of question on in what sense does the evidence probabilistically support a part of a general theory that goes beyond that. Now, that is sort of, as I just said, it is sort of vague. So let me perhaps sort of try to explain it in a different way. If one has a general theory H, and the paradigmatic example is something like, all swans are white. Here on the slide represented as, V of S1 and V of S2, where, S1, S of I is the ith swan, and, W is sort of the white predicate, if you will. And you can basically show it as a consequence of the probability calculus that if you sort of observe the first one and it's white, then the probability of this general theory increases in light of this fact. But is that proposition really the proposition you should kind of care about? This issue sort of appears in Bayesian literature as well, because, for example, when people try to make sense of these sort of probabilistic approaches to induction, sometimes, what people say is that, well, what you should really care about is, in some sense, the proposition that all swans that you haven't seen yet are white. And so then the question is, does observing a white swan confirm that? Or maybe even just that the next one you observe, will be white. Maybe that is really the proposition and the sort of the change in probability that you should be interested in. And the reason why there is sort of a difference between all of these things is because of something which is actually quite understood in sort of the literature on the Bayesian confirmation theory, which is sort of this, the paradox of the transitivity of confirmation. So it can very easily be the case that the piece of evidence increases the probability of a certain general theory, while at the same time undermining some of its implications. So it is actually very, very crucial for thinking about sort of support and confirmation in this Bayesian context to be sort of very, very clearly focused on exactly which proposition you are thinking about, because it can very easily be the case that, this proposition is sort of supported by the evidence, but one of its implications is sort of counter-supported or something like that. There is also the hope that within this sort of Bayesian confirmation sort of theory, one could something sort of akin to inductive reasoning should arise in it. So so people normally imagine, well, could there perhaps be some sort of inductively valid form of reasoning? And the thinking is that perhaps if one chooses the prior distribution for all these theories in the right way, then the kind of inductive-like arguments will emerge in this framework, where it'll be that the probabilities of the right universal hypothesis kind of rise, relative to the sort of the right instances and so on. And so that is kind of the general sort of picture to which this theorem kind of pertains to. And what is kind of interesting about it, just to sort of preempt it a little bit, is that I think that, and this is not a thing that Popper and Miller wrote in any of their work, but I think this theorem sort of allows you to really make sense of the Bayesian theory, this paradox of the transitivity of confirmation, and really kind of see it in this very, very new light. So what argument did they make in their sort of 1983 paper? Next slide. Yeah, okay. So basically, so the problem that kind of exists in this conventional Bayesian way of thinking about it is like, what exactly is meant by the rest of the theory relative to a particular piece of evidence? And their argument was as follows. Well, if I have a particular general theory H and a piece of evidence C, we will basically say that the proposition H or E is deemed to be kind of the deductive content that H and E share. And the proposition if E then H is deemed to be kind of the inductive content of sort of H relative to E. And then their sort of startling claim at the end of that article was basically that evidence always counter supports that proposition. So really, no matter what H and E are, E always undermines anything that kind of goes beyond it in this sort of probabilistic context. Now, what could sort of possibly justify these two particular sort of identifications? And this was kind of the subject of a lot of kind of the subsequent commentary that one can sort of read. Like, this was sort of very, very contentious, because if one looks at H or E, that is a very natural kind of meaning for a kind of a shared deductive content of H and E. Because if, for example, you have an implication of E that is also an implication of H, it will also be an implication of H or E. And in fact, there will be kind of a one-to-one correspondence. Like, all of the implications of H or E are exactly the implications that both H and E share. But that is definitely not true of if E then H, which, by the way, just is really equivalent to just H or not E. You can kind of very, very easily see that there really is no proposition that would sort of capture all the implications of H that are not entailed by E, because one of such implications is just H, and since H kind of implies H implies H or E, it sort of cannot be really made like that. So one of the things that I think we did is that I think we sort of came up with a sort of story that I think makes sense of this particular argument that they made, and I think sort of has some interesting implications. So what is it that we sort of think that Popper and Miller should have said? Well, so why is it invalid to induce H on the basis of E? The reason is because there are possible worlds in which H isn't true that have not really been sort of refuted by E, right? This is kind of the basic reason why like the reason for why people think deductive inferences are valid is because they are thought of as being this kind of necessary truths. Like, the idea is that when you have a deductively valid argument, the conclusion in some sense is valid in exactly the same worlds that the premises are valid in, plus perhaps a couple of additional worlds. And in these sort of inductive arguments are not valid because this is sort of reversed. The conclusions in some sense forbid more than the premises. Now, there is sort of now once one kind of adopts this perspective, it is then kind of, one can then sort of think about what an inductive argument needs to do in a different way. Because if one has, relative to some background knowledge, if one looks at a theory H, this theory H will be true in some possible worlds, and it will be false in others. And in order to convince ourselves that H is true, we basically need to look at, we need to basically somehow convince ourselves that all of the worlds forbidden by it are not the worlds we live in. Now, for some subset of those worlds, it will just be deductively valid to conclude on the basis of E that we don't live in them. So presumably, what induction needs to do is induction needs to explain why on the basis of E, it is valid to conclude we do not live in any of the worlds for which it is not deductively valid to conclude, right? So it seems like relative to E, if we were to induce H on the basis of E, one could kind of divide the possible worlds that H forbids into two parts. Those for which it is deductively valid to conclude that, we don't live in on the basis of E, and those where it would presumably have to be inductively valid to conclude we don't live in them, or that we probably don't live in them. Now, the interesting realization is just that if you look at what the effect of us observing E is on this latter part, on these sort of inductively, on this inductive worlds relative to E, is that once we observe E, their probability actually goes up. That is just how Bayesian sort of updating works. What happens is that once you observe a proposition, all the worlds that it refutes kind of go to zero, and the remaining worlds, their probability just kind of goes up in a completely symmetrical way, sort of pro rata, relative to, by the factor of kind of the worlds that were just refuted. So E kind of has the effect that it increases the probability of any of kind of any world that is not refuted by it. Now, why does that matter? Well, how does that relate with the original argument by Popper and Miller? Well, if one thinks about which proposition in effect makes the claim that we do not live in any of the worlds for which it is that are forbidden by both H and by E. Well, that is just the proposition, H or E. And this other group of worlds for which it's not for which we would need some form of inductive reasoning to conclude we don't live in, those are exactly the worlds sort of forbidden by if E then H. That is kind of really sort of their argument. This argument kind of has sort of two further sort of startling consequences that I think are sort of worth taking a look at. And the first is just the meaning of changes in probability. So to go back to the transitivity of confirmation paradox, next slide. And basically what they show, and this appears in sort of one of their articles, is that if you have a certain proposition, the way it changes relative to observing this sort of evidence C is that kind of this difference is made up of the change in one of these sort of propositions, like sort of X or E, and the change in the value of the proposition of if E then X. And one kind of very, very interesting sort of consequences of that is that if you look at a certain general theory that is supported by the evidence, and you look at some of its particular implication, if the more that implication in some sense just restates E, the more it is supported by it. And the more it kind of just, the more it kind of goes beyond E, the more it sort of, affirms this inductive content of H relative to E, the more it is sort of counter-supported by it. So this kind of, I think, puts kind of a rather stark perspective on the changes in the probabilities of all the implications of general theories, because it sort of shows that kind of the way that their probability changes depends only on the extent to which they affirm the way the extent to which they affirm E, and the extent to which they sort of fail to kind of affirm the rest of H. So that's sort of one interesting way of looking at this theorem. And there is another way of looking at this theorem. Next slide. Which is that one can sort of think of is that one can obtain a slightly different perspective on induction from it. So if one thinks of an inductive argument, one usually thinks of going from, say, E to a general theory H. But quite often it is actually possible to induce a weaker conclusion and then kind of take a further deductive step from that conclusion to the theory. Now, it is kind of very, very difficult to sort of imagine any theory of induction where if it is valid to conclude on the basis of E that H is true, it wouldn't be valid to inductively conclude on the basis of E that some X is true, if you can then take a further deductive inference and go from E and X to H, where kind of X is sort of weaker than H. And so one kind of interesting theorem that one can sort of show about this is that any proposition X that has this property, that it is induced, that one can deduce it from H, and has the property that, like, if we were to induce it from E, we can then make a further deductive inference to get to H, can be written as basically, if E then H, and then you sort of have, and then you have some implication I, which is sort of an implication of this evidence. And what you can kind of sort of see is that, in effect, if one kind of thinks about what is the probabilistic effect by the evidence on all these different propositions, is that it starts negative, and as these different propositions kind of reaffirm E, their kind of support in light of E goes up, and that kind of is sort of what kind of that sort of finishes the talk. So this is kind of the Popper-Miller theorem, I think, stated much better than they stated it, and I think it really does sort of shine sort of an interesting light, a counterintuitive light, on both sort of the interpretation of changes of probability in light of evidence, and sort of the hope of kind of trying to make sense of any sort of form of inductive reasoning in this Bayesian framework. And with that, I open it to questions. Thank you.
Yeah, great. Thanks so much for the talk. I think I have a question to start out with. Hang on, I'll stop the presentation.
Oh, I might want the presentation later, but like, cool.
Yes. Cool. Yeah. So I have a question about the theorem. I'm guessing that if you want to use Bayesianism as a kind of inductive tool, then you would like it to point at a particular theorem. And what you're saying is, or sorry, at a particular theory. So you have some evidence, it refutes some theories, but it doesn't just refute, it also confirms others. So you have, in a sense, an arrow pointing to a particular theory, and that arrow is provided by the probability calculus. But the arrow doesn't exist because all theories that aren't refuted are updated by the same amount. So you don't know which one of them would be the true theory. Is that right, or is it?
I think that is sort of basically correct. I mean, so if you have evidence, you can kind of conditionalize any theory on that evidence. It will increase the probability of any theory that implies it. And indeed, what this theorem kind of shows you is that it will, how much it increases the probability of any theory that implies it, in some sense, depends on how far beyond the evidence that theory goes. The more it goes beyond it, the less it will be supported by it, and vice versa. So there is, it's a very, very, in a certain sense, this whole theorem is just the restatement of the conventional argument against induction in terms of the sort of probabilistic. So the whole idea is, like any general theory, that implies the evidence is supported by it, it is, and the kind of the extra thing it sort of shows is that how much it is supported depends only on sort of how much beyond it goes. Apart from that, that's kind of all there is to it.
Very nice. Okay, if anyone else has questions, then there is an icon or a reaction on Zoom that you can use to raise your hand, and I can pick out your video and unmute you, and you can then ask a question. In the meantime, Lily, you have a question.
Yeah. Could you give an example of this that doesn't take like any algebra or like mathy stuff, or like can you like dumb it down to like kind of like an example or something? Like so you're talking about the white swans thing. So like yeah, so like kind of what's the basic, so like kind of everyone thinks that Bayesian induction works by like you apply Bayesian probability and then you can induce things because then the probability goes up, but then
we seem to have lost Lily.
Yes.
Actually apply the mathematic. Oh, can you hear me?
Yeah,
am I back?
Yeah, could you just repeat the last thing?
Yeah. So where so everyone thinks that in Bayesian epistemology, the probability of is it like the theory being true or like the next observation goes up, and then you're saying like basically if you actually apply the Bayesian, like the math, then it doesn't. But could you it's like very abstract, and I kind of want like a kind of a concrete example to like pump my intuitions or something. So like what's actually going on with the swans and stuff?
So what's going on with the swans is that okay, so you basically want some sort of a kind of a sort of a simpler example of sort of like of these two kind of contrived propositions, if I get that right.
Yeah.
Right. Okay. So well, okay. So I mean, I do actually have an example. It would probably take like a nice blackboard to explain, but just sort of in broad strokes, like what you can sort of take that proposition sort of if E then H is saying is in effect, like what is the probability that you don't live in any world where like you would see all this evidence that you're about to see, but then the theory somehow doesn't turn out to be true, right? And basically, the thing you can sort of see from that is that the probability of that actually sort of decreases. The probability that you live in one of those worlds increases, once you actually get the evidence. Now, that...
Wait, so sorry, the probability that you live in which world?
In one of those worlds where despite all the evidence you have for the theory still isn't true.
And that decreases.
So
it increases. The probability that you live in one of those worlds increases.
And nevertheless, it's not true that all swans are white.
Could you repeat that? Because we only heard the very end, I think, or at least I did.
Oh, so the worlds that Matjaž was talking about are the worlds in which all the swans you have seen are white, but in fact, it is not true that all swans are white. So, and he's asking, what is the probability that you actually live in one of those worlds, given that you've seen these swans, these white swans? Is that right, Matjaž?
Yes, that's basically true. And
so
yeah,
in terms of swans, yeah.
So I mean, again, it's again.
Then what happened?
Sorry.
No, I was just asking. Okay, so then what? So like, why? Yeah, why does it go down?
Well, that's sort of how the math works out. Intuitively, the reason it happens is because like you could have also lived in one of these worlds where you would kind of see a non-white swan in kind of the first couple of observations that you see. Yes.
Yeah.
So I'm just a little bit unclear as to
Yeah, maybe. I mean, I might be unclear on my question. I guess like okay, so like we're trying to figure out the solution to the problem: are all swans white or not? And we like see, I don't know, 10 white swans, and we could have seen swans of different colors, but we didn't. And so so according to the theory,
okay,
all swans are white. Then doesn't that? Yeah.
Right. So let's say that something very, very important depends on, whether the kind of the 1,000th swan that you see is white or not, right?
Yeah.
Okay. Now, you might think, okay, so I've seen a bunch of these sort of swans, and the question is then, okay, so therefore I'm somehow more convinced that this sort of 1,000th swan is white, right? But in fact, the probability of being in one of these worlds where you sort of see a bunch of white swans, but then something goes terribly wrong in the future, has gone up, right?
Uh-huh.
And that is kind of the essence of that whole result. So yeah.
Oh, okay. We have another question.
Yes.
Okay, that tentatively answers my question. By the way, I saw in the chat. Yeah, right. There you go.
Okay, go ahead. You can ask your question. Babak, I hope I'm pronouncing that right.
Oh yeah, that's right. Okay, thank you. I just wanted actually to follow up on this commentary, the question and answer before. So to make the examples more concrete, we have evidence E, we have, I guess, hypothesis H.
That's right.
And then we have a few propositions that are made from, or composed of these.
Yes.
So if E then H is the kind of proposition that you were just talking about. So if I've seen all the white, I've seen swans and they're all white. And my theory is that or my hypothesis is that all the swans are white. So if E, which, all of the swans that I've seen are white, that's E. Then E, if E, then H, you're saying that the probability of this in the light of the evidence, this is the kind of proposition that, if not true, restricts the worlds that I'm living in, right? Yes. Is that what you were talking about?
Yeah, I mean, okay. So the way you just phrase it, perhaps. Sorry, I don't want to interrupt your question, but just if I can just sort of add a note there. So one way of thinking about it is like one can think of that proposition if E then H as kind of the probability that it is valid to conclude H on the basis of E, right? And the probability of that is somehow more likely before E actually comes in.
Right.
That's kind of another way of looking at it. But sorry for interrupting the question.
Yeah, I didn't quite have any question. I was just wanted to clarify this in my own mind. And then the other proposition, which is E or H, I'm not actually quite sure what that means or how to think of that one. So that one is sort of the other way, because is truth value, when E is true, E or H is already true.
That's right.
And that's opposite from E or H, in a sense. Sorry, E, if E, then H.
Yes. So the reason that proposition appeared in their original paper was because that proposition is kind of thought of as the shared deductive content of H and E. So the way to make sense of that proposition is that it in effect just kind of, it's a proposition that says, everything that is jointly implied by E and H is true. That's how one can sort of think of that proposition. Which, in the cases where H implies E will just be equivalent to E, really. And the reason it sort of appeared in their paper is because of that sort of probabilistic formula, because again, there needs to be a way for accounting for, as I think I said during the talk, so one can divide the worlds that H forbids into two parts. Those for which it is kind of deductively valid to conclude on the basis of E you don't live in, and those where it is not. And this sort of E or H kind of in effect says we do not live in any of these worlds that are sort of jointly forbidden by both.
Right.
Does that clarify?
Right. So one way, I guess maybe you also referred to it this way, is that the differences in probabilities that you were showing, something like, basically the probability of H given E minus the probability of H itself, without any evidence. That is sort of the support for H in light of evidence E.
Yes.
Right. And you're showing that support is the sum of those two, or Popper and Miller showed that it's the sum of these two terms, one of which is always positive, one of which is always negative.
Yes.
Right. And so I guess the thing that I'm not quite sure how to understand is this what really inductivists mean, by by support? I mean, we can define this as support, but is this what they usually mean?
So that is so again, this depends exactly on what the question is asking. But so the first issue is this result somehow very, very specific to taking this difference in probability as being the measure of support? And the answer is I think just no. That there are a lot of sort of plausible measures you could take where you kind of get the same effect, because the effect is ultimately, it ultimately boils down to simply this fact that the evidence always increases the probability of basically everything it doesn't refute. So if it would kind of the whole point of inductive reasoning is that you kind of have to make sense of how do I justify to myself that I will disregard the possible worlds where that have not been refuted by anything I have seen so far, but where kind of the things I otherwise want to think aren't true. And probabilistically, those are always supported by the evidence in the sense that their probability goes up. And you can sort of think of many other measures of sort of support where it could be like ratios or logarithms or anything, and kind of that effect will sort of persist there. So in that sense, I think it is whether if the question is like is that identity that I showed just some kind of an algebraic coincidence? That too turns out that the answer to that is sort of no, because I think we actually have a generalization of that identity, which is basically that if one has a proposition and one can has a bunch of propositions that split the content of these propositions, then split the content in this sort of sense that Popper and Miller intend, then basically the change in the probability of this proposition in light of some piece of evidence will equal the sum of the changes in the probabilities of all the propositions that kind of split the content of these propositions amongst themselves. So the reason that identity is true is because those two propositions split the content. So that's kind of that. But again, so sort of these are sort of 2 points. Does that answer your question, or is there?
Yeah, well, I don't know. I mean, as I said, I didn't know if I really had a question. I was just trying to.
Okay, I hope this was useful.
Yeah, it was useful.
Okay, thanks for your question. Then we have Vaden Mazrani. Go ahead.
Hi, thank you for the talk. Can everyone hear me okay?
Yes, I can.
Wonderful. Yeah, so I guess I wanted to just first add another comment for those looking for kind of concrete instantiations of this idea. Something that clicked for me was, I think in some follow-up writing of Popper, he gave the example of, again, all swans are white, but then he gave a alternative hypothesis, which is all swans are white up until the year 2100, at which point they spontaneously turn black, say. And so given the evidence we've seen so far, it's hard to adjudicate between which of these two hypotheses are the, quote, good inductive generalization of the evidence compared to the bad one. And so I guess I have 2 questions. One is, when you speak of many worlds, can I think of this in my head as just alternative general laws which can be deduced from the evidence, or do we mean it more in like the Deutschian sense of the many worlds hypothesis?
Oh, when I speak of many, I really just mean sort of logically possible worlds.
Okay.
So this is usually how probability is interpreted. Did I say many worlds during the talk? I apologize if so. But like the whole idea is so there is this whole idea that one can sort of think of a proposition relative to some background knowledge, or just sort of generically, as kind of partitioning the set of possible worlds into sort of 2 classes, one where it's true, one where it's false. It's kind of unclear if that is in general true or makes sense or anything, but that's kind of the idea. And one can even then kind of interpret probabilities as, being some kind of a measure on this sort of kind of vast space of possible worlds. And basically all of the arguments made in the talk were kind of in that light. Does that answer, or?
Yeah, totally does. Yeah. So then if I'm allowed to ask 2 questions in one go. So I believe in the Popper-Miller Nature paper, it kind of starts with the statement about how Popper's been producing arguments and proofs against induction for 50 years. And so I guess I'm curious why you chose this particular argument out of the various ones that could have been chosen to strengthen and try to popularize, compared to other disproofs of probabilistic induction which Popper has offered. For example, I think in one of the postscripts he offers different
yeah. So okay. So Popper made many sort of disproofs. So for example, one I think disproofs is just this idea that he made this argument that the universal hypothesis should always have probability 0, right? And all of these sort of various arguments have been criticized. The reason we looked at this one is just because we didn't initially understand it. We were able to find some subsequent commentary that we felt didn't quite explain it or understand it. And we thought it would just be valuable to produce a document that would in fact explain it. And I think it's sort of, it is sort of an interesting argument in my view, at least, because again, I mean, as I think I read this book called Bayes or Bust. It's kind of totally, and that book, for example, points out that this argument is just kind of totally independent of all of these sort of concerns about, like, the universal hypothesis have non-zero probabilities and things like that. And it's just, I think sort of kind of, it's sort of an interesting perspective on the whole question. So that's sort of, I think, one question. And did you have one more?
I guess, yeah. Kind of, yeah. So I come from the machine learning community, and I'm interested in this problem of induction because I think if you replace the word induction with like supervised learning, that's directly applicable to what a lot of people are hoping is going to lead to artificial general intelligence.
Right.
And so I think that it's a really interesting project to try to make people realize how relevant this topic is, but there's a lot of, say, philosophical terminology which needs to be, I think, grasped and understood in order to see the relevance in what people are researching today. And so I guess the question is, how do we take these ideas and strip them down so that you don't need to have a background in philosophy and a background in mathematics in order to have people start appreciating how important these ideas are? Because everyone in my community is very interested in Bayesian methods as the thing that's going to get us to AGI, and I think that, frankly, they're delusional, but it's hard to make this point stick. So,
right, okay, well,
yeah,
right, so I love that question, because I think that is just a very, very interesting question to think about. It's not sort of very, very obvious, because I mean, again, I'll be sort of straight up in that I do not know how to do that. If I could, I would just do it. But I mean, I can just sort of offer basically general sort of thinking about that line. So one thing is that kind of Bayesian approaches have, like, their appeal mostly comes from statistics, right? And there is this sort of, for example, this theorem takes place entirely in kind of the realm of propositions, right? And if one were to kind of try to interpret it back in the statistical case, one kind of ends up with a confusion. And so for example, I think that so one approach is to just point out, I think, that statistics by itself sort of doesn't seem to have a hope of kind of generalizing to this sort of other ways of thinking, such as, you know, propositions, logic, anything else that might supersede even that. And then apart from that, I mean, like, so one I think framing of Popper's work in general, if we just sort of move beyond this theorem, is that one way of reading Popper that I like is that like he wasn't interested in sort of questions of justification or questions of like, is knowledge possible or anything of that like. The question was, okay, so given that we assume, say, that knowledge grows in our world, how does that happen? What role do reason and experience play in that? And his perspective, like one way of looking at it, is that it's just in this realization that you know, that reason and experience seem to play more of a critical than a justifying role. And I think one way to sort of confront a lot of these sort of basically AGI theories is to say, okay, you know, great, like this is a particular way of sort of like generalizing the data or updating the probabilities from the data. But the question is, like, can you tell some story about how this process kind of learns the truth about the world in some general sense? And I think that for the vast majority of these probabilistic stories, there just is no story like that. And I think that for a lot of this sort of, I think that there is a story that could be made into sort of Popper style things. Like, so for example, I've been very interested recently in something called fallibly computable functions, which is really a thing that I think basically people that are kind of interested in formal learning theory have also discovered, which is just this idea that, for example, you know, one can imagine computational processes that kind of learn all the uncomputable functions sort of in the limit. Learn certain uncomputable functions in the limit. And I think it is that kind of a story that could, I think, make the difference to that conversation. Because the story is, look, I mean, we can just go on and sort of make up various ways for generalizing the data, as I said, but there has to be a story of how that gets us to something that can just grow towards infinity. And I think that could be a thing that makes a difference. I don't know if that's an interesting answer, but I hope it is.
Real quick question on the tail of that. Sorry.
Okay,
yeah, just
go ahead.
Just like real quick. So if the mathematics does not work out, like you cannot actually do this Bayesian induction because the maths go in the direction that you don't want them to go. Why is it that that people, Bayesians who are trying to do this machine learning stuff, like why didn't they like notice that when they're like trying to program their like AGI type stuff?
Well, okay, so that's okay. That's a good question as well. And again, I think the answer is sort of complicated. So the first thing is that the vast majority of these machine learning applications are very, very sort of specific. They have to do with things like classifying data, or you know, sort of class. For example, there is a lot of classifications, or trying to sort of come up with kind of various generalizations. There is very, very little in sort of the spirit of trying to come up with something that could just kind of learn indefinitely, or like there is no natural reason to be sort of interested in that particular proposition that I mentioned. And again, like as I think I mentioned in response to an earlier question, if you look at sort of at this sort of theorem in the statistical case, there really is no contradiction. So if you looked at this theorem in the statistical case, it would be something like, you know, like, okay, I'm trouble coming up with an example, but basically it would basically come up that some unlikely population, some population with a particular combination of features, let's put it like that, might be more likely once you know something about the population, despite the fact that, you know, some particular subset of that feature combination might now be deemed less likely. And that there is no inconsistency. But what makes that thing work is that you just kind of have frequencies there. And if you kind of look at the whole thing as the statement about those frequencies, like everything makes sense. But when you're kind of dealing with these sort of timeless, non-statistical truths, then sort of things start to kind of acquire this sort of strange perspective on it.
Yeah, the example with statistical analysis is like, so if you imagine that you have a factory that makes these flash bulbs, and these are bulbs that you can only use once, and you want to know how like how reliable they are, like do they actually work? Then you have like this set of like, you know, 10,000 flash bulbs, and then you test 1,000 of those, and that you know that if like you know 10% fail, then you know that kind of represents the general thing. And so like, so that's kind of what you were saying about the, like if you test like a population, like given kind of that, then it's just sort of like given this larger set, like how many, whereas you're saying in this kind of the theory thing, like this, it's not just like you can say like, what is the probability of like of my theory about how flashbulbs are made is true, or something like that? Is that kind of like accurate?
You know, in this sort of timeless case, you know, you only get to live once, right? You know, you don't get to try through various worlds where, you know, in some cases all swans are black, and in other cases there aren't black, and that kind of gives rise to I think this issue. Sam?
Cool. This actually reminds me of a real problem that exists in machine learning, which is that sometimes the machines give trivial outputs. So you have some different functions. Say you're analyzing you're trying to make a machine program that analyzes visuals, and instead of properly analyzing visuals, it just outputs a 0 where it shouldn't, which is kind of related to what you say about like the probability of trivial theories being higher than that of others. So if you have a tautology, then the probability that a tautology is true is 1.
Yeah.
And similarly, I do think that is an actual problem in machine learning. I've heard, at the very least, I've heard people talk about this, and they kind of have to brute force make sure that the machine doesn't go into those kinds of solutions that are trivial and want to exclude them.
Okay, this description doesn't quite ring a bell with me, but I'm sure that something like that might have appeared somewhere.
Yes. At any rate, so Daniel Martin had a question. So go ahead.
Yeah. Thanks for the talk. I've got 2 questions. One is more technical, and one is a question that, if I can try and summarize your talk, and then you can tell me if it's right, what Lily wanted earlier. I do the second one first. So this thing about the swans, can I understand this as a way to explain what you proved is, so if you see the first 100 swans and they're all white, what the Bayesians want is for, as you keep observing white swans, all the hypotheses, apart from the real one, go down, and the real one goes up, maybe indefinitely, but at least in that direction. However, as you pointed out, the hypothesis that, say, after your 200th observation, that the 1000th one is black, but the first 500 are white, goes up. And moreover, or rather, the point is, every observation you make, there will be such a bad theory which does go up. And therefore, if that theory has been going up with every observation you've done, which it has been, then you can't suppress all other theories. Is that accurate?
I'm not quite sure I entirely follow it, but I mean what again, as I mentioned in the talk, it's generally not clear. Like you could disagree about which proposition exactly do you want to go up in probability, or which one you would want to go up in probability. Like it could just be that all the ones you haven't seen go up, or that all of them, or just that the next one. Like you see all of that in the literature. But you seem to have had something different in mind. So which proposition exactly are you asking about?
Say again, sorry?
Which proposition exactly are you asking about?
How do you mean? That was my attempt to give an intuitive overall statement of the. Should I try again, or should I give you my technical question?
Sure, just give it a technical question.
Sure. So I guess I have a confusion. As Popperians, we tend to think of a theory as being something more than just a set of propositions. So like, it's not entirely intuitive that like, so-and-so swans are white, so-and-so swans are this color is a theory to Popperians. But you did use the word theory in your talk and in your maths to talk about some of the variables. So I was wondering, for example, what the difference is between a world in which a bunch of these propositions are true. Let me think. I mean, the technical question is, in your talk, you talked about worlds in which proposition A implies proposition B. Mm-hmm. Is that distinct from a world in which both A and B are true?
I mean, whether a proposition implies one, like whether one proposition implies another doesn't sort of, that isn't the thing that is kind of different from world to world. It's kind of a thing that emerges from,
Right. That's what I would have thought, but your talk seemed to talk about worlds in which A implies B and worlds in which it doesn't.
How so?
So did you use the word implies, or you can deduce one from the other? I'm pretty sure.
Yeah. So worlds where it is. So again, on the one hand you have the worlds. On the other hand, you sort of have the thinker. And if the thinker were thinking in terms of worlds rather than propositions, there are some worlds where after kind of the thinker sees E, where it is sort of valid to conclude for that thinker, okay, we do not live in one of those worlds. And then there are other worlds also forbidden by H, and then worlds beyond that, where kind of the thinker isn't sort of deductively justified in concluding you don't live in them. Mm-hmm. That's, I think, how I meant that.
Okay. Yep.
But okay, it's useful. It's useful to know. That's perhaps a bit unclear.
Yep.
Cool. Okay. Thanks very much for the question. Then I think Sandra had a question. Sandra. Yeah. Like it, sir.
Didn't Kieran have a question as well, by the way? Just
yes,
Kieran doesn't get lost.
Disconnected, I think, and he's back. I'll put him on the list again.
Oh, okay.
I'm back. I can go after.
Oh, you go. It's fine.
Okay. Sure. So this might have been answered while I was disconnected, but you said at one point, unless I'm mistaken, when you get a certain piece of evidence, it raises the probability of all the worlds where that evidence is false. What is there to show? Sorry. It lowers the probability. Wait.
Sorry.
No, I've clearly got mixed up. What's the sentence? How should that sentence end? Sorry, tell me again.
So a piece of evidence increases the probability of all the worlds in which it is true, and it does so in a completely kind of a symmetrical pro rata way if you're using the usual Bayes theorem, and it changes the probability of all the worlds at which it isn't true to 0, And then the factor by which it increases the probabilities of all the worlds in which it is true is kind of the measure of the worlds refuted, so to speak.
Okay, yeah, so you've answered it just in the way you've said it there, because I was wondering why we shouldn't think that it increases the probability of some worlds more than others.
Yeah, well, that just kind of emerges out of how Bayes' theorem works, right? So I mean, again, one sort of interesting perspective to just perhaps add to this theorem is that, like, one of the great appeals of the Bayesian picture is that, like, if you have a proposition and you kind of look at how its probability changes, it can go up and it can go down, and it can, and then maybe at some point it is refuted and it crashes to zero. But when you look at kind of the same graph for any possible world, that's not how it looks like at all. There is no way for it to go, up and down and up and down. It can just go up and up and up and up, and then eventually, when it is refuted, it goes to zero. So this kind of great appeal of the Bayesian picture, this sort of changing in status, like changing in credence, like that, there is no sort of corresponding phenomenon if one focuses on just kind of singular possible worlds. There you kind of just go sort of up and to the right, and then you crash down.
Would another way of saying this then be that objective Bayesianism is false?
Well, that depends on what exactly is meant by objective Bayesianism.
Well, I might be wrong, but I was just taking it here that there's an objectively correct set of priors that you should have. And if that were the case, then wouldn't that provide a way for the worlds to go up and down in the way you're describing? But presumably, from what you're saying, that it's not the case, so that can't be true.
Yeah, it's not how. Again, like, when again, this is, yeah, I mean, this is just how conditional probability works. So like, there really isn't a way in which you could somehow conditionalize, like it's sort of like you couldn't conditionalize the probability of every possible world relative to the evidence. It's just like the way conditional probability is thought to work is that you kind of sort of reduce the probability space, to kind of the space of, given by the thing you're conditionalizing on, and then sort of renormalize inside. And like you could, like it's possible to imagine ways of then kind of shifting probability around, but then that is something other than conditional probability. Like, one of the interesting things that actually came out of thinking about this is just sort of how like non-obvious sort of conditional probability really is. Like if you sort of learn a new piece of information, like, should you really just sort of like just sort of straightforward symmetrically renormalize on everything that remains? Everybody kind of deems that obvious, but one of the things this result makes clear is that it's really kind of not. Anyway, I hope that answers the question.
Yeah, that's great. Thank you.
All right, thank you.
Great. Okay, then we can go on to Sandra.
Hi. So I think I'm still trying to understand the problem. So can I just ask you, is the sort of problem related to the observation that observing a white swan always increases the likelihood that the hypothesis is true in at least one of those worlds, but never speaks to the hypothesis that you yourself are in one of those worlds? Is that...
Not quite. So perhaps state it from that perspective. So the reason, one of the appeals of the sort of Bayesian approach is that if you sort of get a piece of evidence that sort of refutes some section of this kind of possible world space, is that if you then kind of look at all the worlds in which this general theory is true, like, their probability has gone up. And that's kind of one of the things that makes the Bayesian view appealing. What this theorem does is that it kind of looks at it from the other perspective. It looks at what happens, to kind of the probability of sort of the theory being false. And one way of thinking about it is, well, it has just kind of gone down, right? If that the other thing has gone up. But what this theorem sort of shows is that that's not quite happens. Like, one segment of that space goes to zero and the other goes up. And it is in some sense precisely the part which, you would hope the evidence would somehow justify you in disregarding that goes up. And again,
So
this is a trivial fact, but
so you mean it doesn't go down and up by the same amount in those two worlds?
Well,
as in when it goes down in one world,
yeah.
If you think of another world where hypothesis is true, it goes up, but obviously, you know.
So all the worlds that are refuted by the evidence go to zero. All the other ones go up, and they do not go up by the same amounts, but they are scaled by the same factor. That seems right?
That again heavily depends on the priors, right? You would have to know the set.
Well, the factor doesn't depend on the priors, you know, except to the extent that, like basically what happens is, like, so if you have like, if one imagines a kind of an infinitesimal probability associated with every possible world, then if a world is refuted by a piece of evidence E, its probability kind of goes to zero. Yeah. And if you know, this evidence is kind of true in that world, then its infinitesimal probability is scaled up by the factor of something like 1 over P of not E. And the P of not E is determined by the priors. So kind of the integral sort of matters, but the priors sort of inside of kind of the E space don't matter. Like they don't affect the factor by which you scale up or down. Does that answer?
Yeah, I think so. To some extent, at least. Thanks.
Okay, great. Thanks for your question. And then Abel had a comment.
All right.
Yeah, great. Go ahead.
Yes. So I must say, it started when Luli asked her question about why is this not the problem when you actually apply it in machine learning? Because to me, that's exactly the reason why you can call this a paradox. Because it seems to not make sense philosophically, but in practice, you actually can make reasonable predictions in these machine learning cases. And I think, so what I'm about to say comes with a caveat. By now, I've also convinced myself that it might not be true. But at least what I was thinking is that fundamentally, machine learning and Popper are occupied with very different questions, in the sense that machine learning, you do try to generalize, but not to some truth. But you try to generalize to your training distribution, and you still say, well, not my training examples, but the distribution they come from. But that encapsulates all worlds that you could have seen this in. And I think exactly because of that, you don't care if any deduction is valid or not. So you actually get away with making deductive fallacies in machine learning because you don't care about what is true. You care about generalizing to your training distribution, not to some truth that might be hidden in there. Right. And I think this is, to me, briefly resolved the paradox in my mind, but I'm now back into the paradox.
Okay. So, but by the way, can I just make a general comment that I've been loving all the machine learning related questions because this is very interesting. But well, so here's just sort of my point to that. So yes, it's true that sort of machine learning applications seem to be sort of focused on these sort of very, very specific things. But if one were to like invent an AGI, right, that has to be kind of a system that is able of kind of this sort of unbounded, indefinite learning, right? And it, you know, it eventually needs to, you know, like it needs to be possible for it to invent all the theories of physics and chemistry and math and art and just everything. And therefore, like, you know, one can of course always restrict ourselves to sort of some small issue where you know, I mean, even so one way to sort of think about, I think, a lot of these machine learning, you know, implications is like whether or not a given machine learning approach works really just depends on, you know, whether the kind of the right function for your problem is kind of in the relevant search space, and can you sort of find it, right? And with a lot of these things, it's not obvious, like you know, why should there be, like, say, a neural network that, you know, recognizes cats versus dogs, right? And that's kind of separate for whether you find it, but like why should like a 2-layer network of that type exist? And so I think that, like, as I think I was saying before, like there is a like I think that this theorem might apply to some issues in machine learning, and it definitely won't apply to others.
I think that might be exactly a really nice way maybe to separate machine learning from AGI.
Right.
AGI is the part of machine learning where you no longer get away with this fallacy.
Sure, but okay, that's an interesting perspective. But let me just say, it's not exactly obvious to me that even in the conventional machine learning, you can quite easily get away from it. I mean, you can get away from it as long as it is sort of statistical. But I'm not sure if all machine learning is statistical, I guess. But yeah, other than that, it might actually be a very nice way of looking at it. So yeah.
Great, thanks for the comments. Then I think we had Ernst. Ernst had a question.
Yes, thanks for the talk. Interesting. Also struggling a little bit understanding everything, but I was thinking about, so Bayes' theorem as a mathematical theorem in statistics. That's about, if I understand that correctly, it's about how to update statistics when you learn new things, or like how to add together probabilities, right? The original Bayes theorem.
It's it's the original Bayes theorem is a relation that relates conditional probabilities with kind of absolute probabilities and other conditional probabilities.
And this Popper-Miller theorem is not a critique against that theorem, but how it applies to how knowledge grows.
Well, the way to sort of think about it is that it provides a strange interpretation of sort of the changes that theorem gives rise to. But yes, it does not contradict the theorem. I mean, that theorem is just a trivial implication in most kind of axiomatization as a probability. And again, I mean, the validity of the theorem will depend on the particular interpretation of probability you happen to choose. But yeah, in general, it's not meant to contradict those. Like, you know, somebody can just be a Bayesian. The issue is more sort of a can you somehow make sense of like the growth of knowledge or sort of changing attitudes to theories in this sort of probabilistic sense.
Okay, so I have one more question if there's time.
Yeah, go ahead.
So just to make it concrete, let's say I'm a Bayesian and I say that Bayesianism for me means I have a theory. Let's see if the world looks like that theory. So if when I find something that looks like this theory is true, then I think that this theory becomes more likely. If you would put it like, why is that false? How does this theorem say that is an invalid?
Well, it's not invalid. It's more that it's more that it kind of points out to some other things that are valid too. That cast that first thing in a rather different light.
So the thing it points that the theory that it points to theories that are false. The same evidence points also to theories that are false.
That's one thing that you see there. It's not exactly the only thing. By the way, my battery is at 3%. So if there are more questions, I need to run to get a cable so that I don't disappear.
There are more questions.
Okay, I'll be right back.
Yes, we still have, let's see, another 10 minutes. By the way, now that I have everyone here, for future events, you can find us on Facebook. So if you're interested in the third session of the remote reading group, then we'll post an update about when that will be and what the topic of that discussion session will be on the Facebook Oxford Karl Popper page.
Right, I'm back.
Quick question still about that. Will post-quarantine meetings also be available to people that are not in Oxford?
Well, maybe, yeah, because it's actually very nice. I kind of like it. To be announced. But yeah, again, if so, then you can find it on the page.
All right.
Cool. Okay. We had another question from. Let's see, it was Antonio.
The next question's from
I think Antonio Santellos. Go ahead.
Hello there. So the way we're now framing the situation is as if we already have a given set of hypotheses, and the problem is how to assign probabilities to them. But from an AGI perspective, I think that the main problem is how to generate a new hypothesis, how to make a conjecture. Would you like to comment upon that? Is there any way there could be an algorithm that can generate a conjecture given the evidence? Or, how do you navigate the space of infinite possible conjectures you could make?
Right. Okay, well, that is not sort of, I think, directly related to the theorem, but it is, I think, just a very, very interesting question in general, right? So I think that like if one sort of, for example, if one sort of takes von Popper's work as sort of the foundation, right? The idea there is that theories are just obtained by some sort of variation. And they just sort of arise, and like the whole idea is not to kind of come up with them, but rather to recognize them as valuable or relevant to some problem when they do. Now, how that happens is pretty mysterious. I think I mentioned some of these sort of formal learning theory approaches that I think sort of also kind of present an interesting, like they give an interesting sort of perspective on that issue. I think that, I mean, on the whole, though, it is, I think, just sort of a very, very interesting and I think somewhat understudied mystery of sort of how to sort of think about that problem. Now, I realize that in some sense, machine learning, right, is again sort of focused on those types of approaches, like how do you sort of generate theories? And again, I think that the question that should always be asked by this approach is I think a very, very useful thing to always ask is the sort of universality question. Like, can this way of generating hypothesis somehow, take you to this infinity where you sort of come to understand the world in its infinite complexity or something like that? So that would be my comment. Is that useful?
Yeah, I don't have the answer yet, but yeah, I think that's a crucial problem to solve.
Yeah.
So Jonathan asks, inspired by your mention of infinitesimal probabilities, is it possible after a probability goes to 0 in some world for it to return to a non-zero positive probability?
Well, not in the conventionally imagined, because see, in a lot of these sort of like in a lot of these sort of applications of Bayesianism, right, the evidence is sort of taken as this infallible thing that you sort of conditionalize on, and once you do it, it's sort of done. Now, it is possible to sort of imagine, all manner of sort of, fallible ways in which you might update things, then sure, these sort of probabilities can very easily come back from 0. But it sort of all depends on somehow being able to change your mind about this infallible evidence that somehow came in.
And I suppose this relates to the Duhem-Quine thing, and that's kind of outside the scope of what the Bayesian stuff.
Sure, I mean, it relates to fallibility, just how you think about sort of the way you come to experience the world in general. Yes.
Okay, then, unless there's any other questions, I think I have a final question.
Okay.
Is that why do you necessarily need the probabilities to go to 0 after the evidence is being provided? Can't you say that, for example, you're not exactly sure whether you measured or whether you observed the evidence, and therefore the right. probability that the evidence is correct is
right. So that's actually kind of interesting, because I gave a version of this talk earlier at some point in December, when an audience member basically pointed out sort of something similar, like, look, can't you just kind of say that, basically the probability that E is true has changed from, say, 40% to 80%, and just kind of renormalize there, and then kind of renormalize again outside it in the same way. And at the time, I was sort of like, okay, well, that sounds interesting. And one of the things you realize if you do that is that you get this exact same effect just repeated all over again. Because again, it's just how the math works out. But basically, if you do any kind of conceivable sort of alternative way of sort of renormalizing, you know, like if instead of this goes to 0, it goes to something else, but kind of everything is done symmetrically, you get the same, you just get basically the same theorem all over again.
Yes.
But I mean, for simplicity's sake, I think it's kind of sensible to keep it this way.
Yeah, even if the probabilities don't go to 0, induction is still false, so we don't have to worry.
I suppose.
Cool.
All right.
Okay, well, that's it for this session. Thanks everyone.
I have a dumb question. Can I have one more question?
Yeah, okay, well, go ahead.
Okay, it's a dumb question though. Does this mean that according to Bayesianism, we do in fact...
It was too much for the internet to answer this question.
All right. Well,
oh, sorry. Did it cut out?
Yes.
Yes.
Oh, am I here now?
Yeah, you're here now.
Okay. So according to Bayesianism, do we in fact live in an anti-inductive world?
Well, that sort of depends on what exactly is meant by the anti-inductive world, right?
Because the probability goes down. So like there's a kind of a standard joke in Bayesianism, like, oh, we might be living in an anti where everything is upside down, and you're saying actually that's true.
Well, yeah, right. So one way to read Bayesianism is basically, you know, everything that hasn't been refuted yet has been increasing in likelihood since the beginning of time. That is kind of a way of looking at it. I mean, another perspective, just to sort of say, right? So you could sort of think, well, so for example, like for example, at some point I had a conversation with a Bayesianish type person about like how you might make sense of this whole idea of the growth of knowledge in the Bayesian context. And basically their statement was, well, it's kind of like it's you know, the knowledge grows as sort of the probabilities of false theories go to 0 and probabilities of truth theories go to 1. And one thing you can kind of point out about that kind of argument is that, well, even if that happens, that convergence is very, very non-uniform, right? So there are false theories that have been increasing in probability since the beginning of time and will just keep doing so for the next thousands of years. And conversely, you know, there are false theories like truth theories that have been decreasing in probability since the beginning of time and will for thousands of years, but are still sort of true or false. I mean, I suppose maybe the exact same criticism can be levied against any other theory of the growth of knowledge, but it is an interesting one to sort of point out nonetheless. So yeah.
Cool. Okay. Well, thanks again, Matjaž, for joining us and for giving this talk. And I, for one, very enjoyed it. I think everyone here, thanks for coming.
Yeah, I mean, I loved it. I really love the questions. And if anybody like wants to connect, just send me an email or message or Twitter or anything.
Yes,
so, yeah.
We'll share your information, your Twitter profile on Facebook so people can find you. And yeah,
Thank you.
Thanks again to everyone for coming, and hope to see you at the next event.
Thank you. Thank you so much.
Yeah, bye-bye.
Bye.
Thank you very much. Bye.